This week has been all about the fundamental theorem of calculus, and there are two parts. First of all, what we need is a continuous function on a closed interval and any value from that closed interval. So when we say closed interval, this means that the endpoints are included. It's an interval that includes the endpoints. That's the closed part of it. So we're saying all the x less than or equal to b and greater than or equal to a. In between a and b and including a and b. The other version of this would be an open interval, which does not include the endpoints. An important thing about a closed interval is that there is a smallest value. This interval has a smallest value. An open interval does not have a smallest value. We have a lower bound, but we don't have a lowest value. There is no smallest real number after a. So a closed interval has a smallest and a largest value. An open interval does not have a smallest or a largest value. So that's one of the weird things about open intervals. It does not contain a smallest or largest value. So once we have a continuous function on a closed interval and any value from that closed interval, we get two parts of the fundamental theorem of calculus. The first, we use an antiderivative to calculate a definite integral. Say the definite integral from a to b of f of x to x is capital F at b minus capital F at a, where capital F is an antiderivative of f. That is, capital F prime is f. We are using an antiderivative to calculate a definite integral. This is important because we want to find area. We want to calculate a continuous sum. This is one way we can do it. This is how we do it. We find an antiderivative. The second part gives us this in reverse. We can use a definite integral to construct an antiderivative. This is the part that says every continuous function has an antiderivative. Sometimes we have to construct it. Sometimes we have to approximate it. The reason that we say that this means we can always construct an antiderivative is that we can always calculate a definite integral because it's just a continuous sum. It's just an area. And we can always do that. Depending on how well we know the function to any degree of accuracy. We've been using this to combine with what we know about sign, direction, and concavity. When the derivative of a function is positive, then we say that the function is increasing. What we have added to that with our fundamental theorem of calculus is that when the derivative is positive, the function is increasing, and the area tells us how much. When the derivative is negative, then the function is decreasing. The area tells us how much. So that's the part that we've added. We've talked about that before. F prime positive means F is increasing. The area under F prime will tell you how much the function increased. The place we want to see how much the function increased is right here. Capital F at B minus capital F at A. F at B, that's where the function ended up. F at A is where it started. Maybe I should do this in mean format. Where it started, capital F at A. Where it is, capital F at B. I've been trying to figure out how I can distill, instead of making like these like 45-minute videos and just throwing them up on YouTube of me talking, chopping them up into little 1-minute bits and then putting them on TikTok. Oh, wait, or whatever comes after TikTok, apparently. Ooh. Any questions? Now I'm gonna have to see if this video doesn't go up on YouTube. It's like, you said TikTok. It's like, they're also jealous. Like on TikTok, you can't say like YouTube. Like, oh, I made a YouTube video. Because it's like, oh, linking to another video site. So jealous. All right, what are we talking about? Oh, yes. So if you would recall, if you would recall, we have been playing this game where I give you a function and say, here's the antiderivative. I want the function we're interested in, capital P of X, is an antiderivative of little p of X, and then I give you the graph of the derivative. So the point is, you are looking at the graph of the derivative. And then I ask questions: increase, decrease, concavity. Look at the area to figure out how much things are changing. So the other way that we can do that, instead of just saying that capital P is the antiderivative of little p of X, such that capital P of 0 is equal to -2 or 1 or whatever it was, we define the function differently. We use the second fundamental theorem of calculus and say capital P of X is the definite integral from 3 to x of P of t dt. And then I show you the graph of little p of X. So the important thing to recognize here is that if capital P is this definite integral from 3 to x of P of t dt, this down here is the graph of capital P prime of X. Another thing to note is that when we define things this way, we say capital P of X is the definite integral from 3 to x of little p of t dt. I've changed the variable there from a t to an x because I'm going to be plugging x into the t. And we don't want to take x and plug it into an x. It becomes like this very being John Malkovich situation. So we use this alternate variable. So we're not plugging x into x. So that's all that's going on with this p of t dt. Any questions? Comments? Slide remarks? How's everybody okay? We just need to get through tomorrow. Stop asking. I had one student one semester kept track of every time I asked, is everybody okay? It was a lot. It was more than the number of classes because it happens a lot. They also kept track of how many times I said, how's everybody today? This told me some very important information. My class is very, very good. I'm just going to start counting the shit that Leach says all the time. I think at one point they started to count the number of F-bombs that I dropped during class, but the number was too damn high. How many times Leach swears during class? No, there's just too many. So I got this problem. I'm going to give you a few minutes to take a look at it, and then we're going to break into teams, and then we're going to make sure that we can all do this problem. That's the goal. We all have to be able to do the problem.
Is it under Zoom?